You know, every single time you shop online or check your grades or even book a flight, you're talking to a database. And yeah, they look like just simple tables, right? But underneath all that, there's this incredibly powerful, super elegant mathematical language doing all the heavy lifting. So today, we're going to go on a little journey. We're going to uncover that secret language and really see the hidden structure that basically powers our entire digital world. Let's pull back the curtain and see how this whole thing actually works. So, let's start with our central piece of evidence, a student database. I mean, this looks pretty familiar to all of us, doesn't it? It's just a table. You've got your columns for name, ID, major, and GPA. And of course, each row is just a single student. Seems almost too straightforward. But believe me, this simple grid is the key to absolutely everything. And that really brings us to the big question, right? How can something that looks this simple handle the massive, unbelievably complex information of our modern world? What is that hidden engine? What's the mathematical blueprint that gives this simple-looking table its incredible power? Well, that's the mystery we're about to solve together. Okay, so to kick off our investigation, we've got to look a little closer. We're going to peel back the very first layer of this database and find its most basic, most fundamental component. You know, the best way to understand any complex system is to just break it down into its smallest parts. So let's zoom right in on our table and focus on just one single row, the record for just one student. So in the world of math, this one single row actually has a very specific name. It's called an n-tuple. And really, an n-tuple is just a fancy way of saying it's an ordered list of elements. In this case, since there are 4 pieces of information, the name, the ID, the major, and the GPA, it's what we call a 4-tuple. And here's the absolutely crucial part. The order matters. It matters a lot. The name always comes first, the ID second, and so on. And boom, just like that, we've hit our first big discovery. Our entire database table isn't just some random collection of data. It's a collection of these perfectly structured 4 tuples. Every single row is a self-contained, ordered packet of information. That's the first secret. Okay, so we know each row is a tuple. Cool. But where do these specific tuples even come from? Are they just chosen at random? No way. Their origin is actually the key to something way, way bigger. All right, this brings us to a really cool concept called the Cartesian product. I want you to imagine you have a set of all possible student names in the world, and another set of all possible IDs, all possible majors, and all possible GPAs. The Cartesian product is the math operation that creates this gigantic, enormous set containing every single possible combination of those things. It literally creates a universe of all potential student records that could ever possibly exist. Let's look at a super simple example to see how it works. Say set A is just the numbers 1 and 3, and set B is the letters A and B. The Cartesian product, A times B, just pairs every element from A with every element from B, so you get 4 possible ordered pairs. But notice, if you flip it, B times A gives you a totally different set, which just proves it again that order is absolutely critical here. I just love this analogy. Think about it like this. The Cartesian product draws a map of a giant, unbuilt city grid. It shows every possible street and every possible intersection. Our actual database, the data we actually care about, is like us choosing which specific roads we want to pave and which houses we want to build on that grid. And that right there brings us to the big aha moment. This is where we connect that massive universe of possibilities, the Cartesian product, directly to our specific real-world student table. This is where the magic really happens. See, in mathematics, a specific chosen piece of a Cartesian product is called a relation. And that is exactly what our student database is. It is a relation. It's a carefully selected set of tuples that we've picked out from that enormous universe of every possible student tuple. And you know what? This simple, powerful idea is what won out against all these other, way more complex models of storing data. So here it is, the key takeaway. A database isn't just a table. It's a formal mathematical relation. It's a small, meaningful island of reality that we've literally plucked out of an infinite ocean of possibility. That's the core concept that makes the whole thing work. And because it's this formal math object, we can represent a relation in all sorts of different ways, not just a table.
We could use a matrix of ones and zeros to map out which connections exist, or we could even visualize it as a directed graph, with nodes and arrows. It's all describing the same underlying structure, which just goes to show you how versatile and fundamental this whole idea really is. Okay, so we've uncovered the structure. We know a database is a relation, which is just a set of tuples. But so what? Why does this formal structure even matter? Well, now we get to the payoff. This structure is what lets us actually do things with our data, and do them with incredible speed.
Yeah, this whole mathematical foundation isn't just some academic exercise. It's what gives us the power to query our database, to ask it really specific, complex questions and get precise, reliable answers back. This structure is the reason databases can sift through billions of records in milliseconds. It's the engine behind query languages like SQL that run, well, so much of the modern world. Let's see how. Let's say we want to find the names and GPAs of all the computer science majors. We do two core operations. First, we apply a selection. Think of this as the where clause in SQL. We go through our whole relation and select only the tuples, the rows, where the major is computer science. Then, from that smaller group, we apply a projection. This is like creating a shadow of the data. It's the select part of a query, showing only the columns we actually care about, in this case, just the student name and GPA. And there you have it. That's our result. By applying these two mathematically defined operations, we have a brand new, smaller relation that perfectly answers our question. This is the power of that hidden structure. It's not just about organizing data. It's about giving us a reliable, repeatable, and just blindingly fast way to get the exact answer we need every single time. So when you get right down to it, a relation is so much more than just a term in a math book. It's the fundamental grammar that lets us have a structured conversation with our data. It's the invisible architecture that holds up so much of our digital lives, from social media feeds to global finance, all because it provides both structure and just unbelievable efficiency. So the next time you see a simple table of data, I really hope you'll see it a little differently. You'll see the tuples, you'll imagine that vast Cartesian product it was pulled from, and you'll see the elegant relation that it represents. Now that you know the secret, what other relationships in the world's data are you going to see? Thanks for joining me on this one.